All right, hello, this is worksheet 15.7 on cylindrical and polar coordinates. I don't think I have much to say, so let's get started. Oh yeah, I do actually have one thing to say. At the top of this worksheet, it did explicitly say not to compute any integrals, or just to worry about setting them up. I'm still going to show some of the computations just so that you can check those with the final correct answer. But I wouldn't worry as much about that. In any case, let's get started with number 1. We have this integral in Cartesian coordinates, you want to convert it to cylindrical coordinates. Okay, so the first thing I'm going to point out here is we have dz as our innermost integral here. Whenever we have dz as the innermost integral and we're converting to cylindrical coordinates, we can just do a direct conversion. And so by that I mean this 0 to x will become 0 to r cosine theta, that's equal to x in cylindrical coordinates. This x squared plus y squared is r squared, and this will become r dz dr d theta. And so whenever we have these z bounds in cylindrical coordinates, or in Cartesian coordinates, we can directly convert it to z bounds in, that's too fat. We can directly convert these to our z bounds here in cylindrical because it's the same z coordinate. And so that's a really nice advantage of converting between Cartesian and cylindrical coordinates. Once we've done that, we need to set up the x and y bounds. And so now we're going to focus on this part of the integral where we have y going from -1 to 1, that's here to here, and then x going from 0 to root 1 minus y squared. And so we should probably figure out what curve this represents here. Hopefully we've found out by now that if you have something to equal the square root of a constant minus another variable squared, then we can square both sides, put all the variables together, and then we get a circle of radius 1. We only want the right half of the circle because this square root is always positive. So we only want that part of the circle, but we still have a circle. Draw that a bit better. Okay, it's radius 1. And so now we just need to set up the r and theta integrals, but these are relatively straightforward for circles. As we saw when we were doing polar coordinates, we want to find the minimum value for theta. So the minimum value for theta is right here when I'm all the way down here in my region, and then it can sweep all the way around my circle up to here when it's straight upward, because we're trying to do this whole region here. So the minimum value for theta is -pi/2. The maximum value is pi/2. And then for the radius, it's just going to be 0 out to the radius of the circle, 0 to 1. Because we can start in the center here at 0 and then move outward towards 1. Okay, and so now we just evaluate this integral to get the volume. We should do the innermost integral first. Integral -pi/2 to pi/2. Integral from 0 to 1. Integral of, this is all a constant with respect to z, so this just becomes r to the 4th times cosine theta. And now that these are constant bounds, we can separate this into 2 separate integrals. And then this one from 0 to 1. And then if I just do these in my head real quick, that first one is 2, I think. And then that second one is 1/5. So this is equal to 2/5. Great, okay. I think that's all we have to do for this problem, so let's move on to the next one. Number 2, suppose a is greater than 0. We want to find the volume of the region cut from a solid sphere, rho less than or equal to a, by these 2 half planes in the first octant. Okay, so let's try to draw this picture. We have a solid sphere. We just want the first octant, so that's this, so we might even want to imagine that we just have a hemisphere like that, and it's cut between the half planes theta equals 0, that's here, and theta equals pi over 6, that's here. So let me draw this out a bit. Okay, so it's that part of the circle, and maybe like me drawing this isn't a very good, maybe my sketch isn't very good for visualizing. But in any case, we want to try to set this up in either spherical or cylindrical coordinates. Probably not Cartesian. There's a circular object here. We probably want to do spherical or cylindrical. And we're going to try to set up that integral so that we can get the volume of this region. I always like to start when I'm doing this with identifying which intervals are constant. So let's start with theta first. This one's sort of the easiest because it gave it to us. It told us that theta is between these two numbers. So I know that 0 is less than or equal to theta, which is less than or equal to pi over 6. Okay? And now what we can do is we can try to imagine what these cross sections look like for a fixed theta. No matter what theta is, that's just going to look like a quarter circle. If you take any cross section along these purple planes, your sphere is just going to look like a quarter circle, which is nice because we know how to set those up in polar coordinates. We know that this angle here can range from straight up to straight horizontal, like that. And then we know that the radius goes from 0 to a. Remember, this has a radius of a. So that tells me that rho goes between 0 and a. And then phi goes from 0 to pi over 2. Because here, when we're in spherical coordinates, this angle is phi. All right, so then let's go ahead and write out that integral. This will be integral from 0 to pi over 6, integral from 0 to pi over 2, integral from 0 to a of rho squared sine phi d rho d phi d theta. Okay, again, our bounds are constant, so we can split this up into 3 separate integrals. And then so let's just do that. Yeah, and then the theta integral is not very difficult because there's no theta inside my integrand. So that'll just become pi over 6. The rho integral is that. And then the phi integral is just this. Okay. And so let's see. The rho integral is going to be a cubed over 3. That's going to be pi a cubed over 18. And then the phi integral, I know that's just going to be 1. And so my final answer is pi a cubed over 18. You could verify that geometrically. It turns out if you work through like this shape of the circle rigorously, it ends up being equal to 1/24th of the volume of the sphere, which is indeed equal to what? Let's see, 1/24 times 4/3 times pi a cubed, which is indeed equal to pi over 18 a cubed. And so that's good. That's what we wanted. We did it correct. This is just a nice sanity check at the end. All right, let's move on to number 3. We want to find the volume of the solid cone that lies within this sphere above the xy plane and below this cone. Okay, so a few things I'm thinking first here. Here I have an x squared plus y squared plus z squared, which is making me think spherical. But here, z isn't squared. And whenever we have something where z isn't squared... Oh no, I dropped my stylus. Give me 1 second. Whenever we have something where z isn't squared, we want to try to think about cylindrical. We could square both sides of this equation to make z squared, and maybe that would give us spherical. But this one we could either take as cylindrical or spherical. I think it's always good to start by trying to identify which coordinate system you want to set up your integrals in before you start the actual problem. With that said, let's draw the system now. So we have a sphere. I'm actually going to draw my coordinate plane first. So we have a sphere, that, and then we have a cone. It goes in this direction. In cones, by convention, they go in both directions. Okay, and so we want the volume of the solid that is inside the sphere, above the xy plane, and below the cone. So that is going to be this region right here. Okay, and so again, we're going to try to figure out what the bounds are on this. I'm going to try to do, this seems like it'll be annoying to do in cylindrical coordinates because there's a sharp corner here where we'd have to change the z bounds. So I'm going to try spherical. The first thing I noticed in spherical is that this object is symmetric if I rotate it about the z-axis, and whenever that happens, I immediately know that theta is between 0 and 2 pi, which is very nice. Now, for any one of those values of theta, we can imagine what the cross sections of this shape look like. We'll have the cone, which goes up like this, and then we'll have the sphere going out like this. The sphere has a radius of 2, and so this should also have a length of 2. Okay, and so now we want to try to set up this region in polar coordinates. So we need to, in particular, we know that this is going to be constant bounds in polar coordinates because it's just a circular arc. So what we need to do is we need to find what this angle is, because that's going to be our upper bound on phi. And actually that's really all we need to do, because we know rho goes from 0 to 2. Because this is a circular arc of radius 2. Alright, and so now we just need to find what that angle is. The good news is that we can find the slope of this line here. Whenever we do theta cross sections, this direction is the r-axis and this direction is the z-axis. And so what we have is that we have from here, that cone, it's actually given by z is equal to r. And so that is a line which has a slope of 1. And whenever your line has a slope of 1, this angle here is going to be 45 degrees. In general, that angle is going to be, I'll call this one phi 0. In general, phi 0 is going to be arctan of, is it slope or 1 over the slope? 1 over the slope, which is equal to arc cotangent of the slope of your line. But here it's relatively straightforward to get because it's just a slope of 1. Okay, and so that tells me that my phi angle, it starts at pi over 4 and goes up to pi over 2. All right, so that's all that. Now we can set up the integral. Let's see. Theta goes from 0 to 2 pi. Phi goes from not 0, pi over 4 to pi over 2. And then rho goes from 0 to 2. And we just want the volume. So it's rho squared sine phi d rho d phi d theta. Okay. Once again, the theta integral is the easiest. That's just 2 pi. The rho integral is also going to be relatively straightforward. That is going to be 8 over 3. And then I'll actually do the phi integral just so that I know I don't make a mistake. If I do that, I get 16 pi over 3 times, okay, let's see. Integral sign is cosine or negative cosine, but then I'm going to use the, I'm going to swap the order on the bound so that I don't have a negative sign. Okay, cosine of pi over 2 is 0, cosine of pi over 4 is root 2 over 2. And so this is equal to 16 pi, or I guess I'll do 8 pi over 3 times root 2. That is my volume. Great, okay. Let's move on to the next one. Number 4, we want to find the volume of the region bounded above by this paraboloid, below by the xy plane, and outside this cylinder. Okay, so I'm going to sketch this again real quick. We have a paraboloid which goes downward. We have a cylinder, x squared plus y squared equals equal to 1, so I'm going to draw that in, let's do purple. Okay, and then I think that's it. So we want the region that is bounded above by that paraboloid, below by the xy plane, outside the cylinder. So that is going to be these regions here. Okay. So now, again, the first thing I'm going to notice is that if I rotate this about the z-axis, my region doesn't change. That immediately tells me that theta is between 0 and 2 pi. And so then I have the, I can look at the cross sections that are formed when I do that. And let's see, I want to go outside the cylinder that has a length of 1. And under this paraboloid, so that'll be this region right here. Okay. And so now I want to try to decide whether I want to do this in cylindrical or spherical. And essentially that amounts to, do I want to set up this 2D region in Cartesian or polar? I'm just going to say right now, that one looks like it's going to be really annoying to do in polar. That one looks a lot easier to do in Cartesian. To do Cartesian, we need to get the equations of the two lines that are bounding our region. But fortunately, that's not too difficult. The paraboloid is z equals 9 minus r squared. And the cylinder is just r squared is equal to 1. And so here our lines are, this one is r equals 1. And this one is 9 minus r squared. And so where does that intersect with the r-axis? That'll be when r is 1 and r is 3. So r is between 1 and 3. And then z goes from 0 along any of these z cross sections. Z is 0. And it goes up to 9 minus r squared. So if we write out that integral, we're doing cylindrical coordinates. Theta is 0 to 2 pi. R is 1 to 3. And z is 0 to 9 minus r squared. And that will be just the volume, yep, r dz dr d theta. Again, theta is easy because it doesn't appear anywhere there. That's just 2 pi times, okay, I actually have to integrate this back to z, so that'll be r times just 9 minus r squared dr. And now I just need to do this integral. I'm going to do it with a u sub because it turns out to be a bit easier and I'm lazy. So I'll say u equals 9 minus r squared. You could just FOIL out the polynomial, but I don't want to do that. So du, I'll say negative 1/2 du is equal to r dr. And so this will be, I'm going to use the 1/2 to cancel out the pi. And I'll use the negative sign to flip the bounds on my integral. So let's see, when r is 1, u is 8. And when r is 3, u is 0. And that'll just be u du. And so that's easy. That's pi over 2 times 8 squared, which is 32 pi. Yay. Okay, that's that one. Let's move on to number 5. Where we want to find the volume of the solid that is between those two spheres outside of that circular cylinder. Okay, so let's draw this. We have two spheres that are concentric. And then we have a cylinder. So this is sort of a complicated problem. And we want the region outside of the cylinder, but between the two spheres. So that's going to be this region. And again over here. And then again, I'm going to think about, does this have rotational symmetry? Yes, if I rotate it by an angle theta, this picture will remain unchanged. And so theta, again, is going to be between 0 and 2 pi. From there, we're going to consider a theta cross-section, which it tells us to do in the hint, but we would want to do that anyway. And if we do that, again, this will be my z-axis. This will be my r-axis. And let's see, we want to stop at 1, because that's where my cylinder is. And then we have a circle of radius root 2, which I'll draw like this, and a circle of radius 2, and we want this region. Okay, so we could think about what coordinate system we want to use for this. I personally think it looks like it'll be easier to do this integral in cylindrical coordinates, which corresponds to doing this in this 2D region in Cartesian coordinates. So let's do that. First, we'll start with our R bounds. So R can be between, let's see, right here, R is equal to 1, and up here, R is 3. So it's equal to 2 up there. Being silly. Here it's root 2. Okay? And now we want to find our bounds for Z. And if we start drawing our cross sections in the Z direction, we run into a bit of a problem. It's always bounded above by this curve, Z squared plus R squared is equal to 2. Or sorry, is equal to 4. So let's see, if this curve is Z squared plus R squared is equal to 4, then Z is going to be root 4 minus R squared. But the curve that's bounded below by changes when R is between 1 and root 2. So that's in this part of the region here. It's bounded below by the other semicircle, which can be root 2 minus R squared. But that's only when R is less than root 2. When R is greater than root 2, then Z is between 0, and the lower bound for Z is 0. So 0 less than equals Z. It's still bounded above by the outermost sphere, but it's bounded below by the xy plane. And so we'll have to set this up with two integrals. The volume, first we'll do the theta one, which is easy. And then we have to do R. And then we'll do Z, which is root 2 minus R squared to root 4 minus R squared, R dz dr d theta, plus, and then the exact same thing, but this should be 2, the innermost integral, no, yes, that is right. Yes, okay, the innermost integral lower bound is 0. And we can compute this integral. I don't really want to. I'm going to do some scratch work over here. I'll show you why in a second. We want to find the integral of the square root of a minus r squared times r dr. To do this, we'll do a u substitution. And so this is negative 1/2 integral of, I think that's just root u du, which is negative 1/3 u to the 3/2. And we substitute in u, that's negative 1/3 times a minus r squared to the 3/2. And if we differentiate that, we do see that we get the original integrand back. And I guess I should say plus c. And so now if I go back to doing this, the theta integral is easy. It's just 2 pi. And now I have to do the r integrals, or the z integrals, which are also easy because they're just, the integrand is constant with respect to z. And then we'll see here why I did that integral on the side. So that minus 2 minus r squared r dr plus integral from root 2 to 2 of r times the square root of 4 minus r squared dr. Okay. And then just as a quick simplification, because it'll make my life easier, I'm going to combine the first and the last integral. That'll be integral from 1 to 2 of r times the square root of 4 minus r squared dr minus integral from 1 to root 2 of r times the square root of 2 minus r squared dr. Okay, and I did those integrals earlier. It's just negative 1/3 times a minus r squared to the 3/2. So let's see, negative 3/2 times 4 minus r squared from 1 to 2 plus 3/2 times 2 minus r squared no, these are 1/3 raised to the power of 3/2. Okay, from 1 to root 2. And then we just evaluate that. That is 2 pi times negative 1/3. I'm actually going to move around some of the negative signs. So that is 3 to the 3/2 over 3 on the first term. I think that's what you end up getting. And then the second term is minus, oh, okay, it's 1/3. Okay, I did the mental math wrong for a second. I'm like, oh no, I messed up. Okay, so that's 2 pi over 3 times 3 root 3 minus 1. And that is our final volume. I think this one's probably the most involved one of this worksheet, but it's a good problem to work through once. Okay, and then number 6, oh no, what happened? Number 6, we are given a right circular cylinder whose base is this circle, which it tells you about that. It tells you that it's that circle later in the problem, and whose top is the plane z equals 4 minus y. And so what to imagine is we have this cylinder, I'll draw it in purple, over here, and it goes up until we get to the plane z equals 4 minus y. So that'll point downward in this direction. Okay. And so now first we want to find the volume. I think this is a natural spherical coordinates question because they gave us what the base of the region is. So we're already looking down in it from the z direction. So I want my innermost integral to be with respect to z. And I can normally, actually, we'll skip this for now. Let's do r dz dr d theta. And so now I just need to parameterize that region with r and theta to get my 2D integral. This is a polar integral that we may have done before. It's a bit of a tricky one sometimes. Actually, no, this one's easy. It's cosine that's tricky. Because theta starts at 0, goes all the way around, up to pi. So then theta goes from 0 to pi. And then r, well, they gave us the formula for r. This curve, oh no, why do you keep doing that? Stop it! This curve is r equals 2 sine theta, and so our bounds from r are just 0 to 2 sine theta. And then we can worry about our z. For the z, the lower bound of this region is just the xy plane, and it goes up to the top of our region, which they gave us. It's 4 minus y. This is 0 to 4 minus y. Y in spherical coordinates is r sine theta. And that's all we have. Okay, so let's do this integral. Integral from 0 to pi to 0 to 2 sine theta. And then r times 4 minus r sine theta. dr d theta. Right, now we do the r integral. I'm going to distribute this r. So this is integral from 0 to pi. Integral from 0 to 2 sine theta of 4r minus r squared sine theta dr d theta. Then we do the r integral, and we get, let's see, this is 2 times r squared minus 1/3 times r cubed Okay, and so then that is integral from 0 to pi of 4 sine squared theta minus 2/3, wait, the cube should be on the outside here, 8/3 sine 4th theta. Okay, and now this is an ugly integral. I sort of just happen to know what it's equal to because I do these integrals a lot for my physics classes, but we'll work it out on the side here. Sine squared theta, we'll use the power reduction identity. Get 1, I think it's minus cosine of 2 theta. Yep, that's right, all over 2. The cosine part of the integral goes away, so we just get pi over 2. And then we do something similar, sine of 4 theta, except we do the power reduction identity twice. So let's see. This first term is 1/4. The second term is going to be something proportional to, I'll just work it out, plus 1/4 cosine squared of 2 theta. And then the mixed term is going to be something proportional to cosine of 2 theta, but we know that that integral from 0 to pi is just 0, or at least I know that. And so I'll omit that term. And now we do the power reduction again on cosine squared. So that's 1/4 plus 1/4 times 1 plus cosine of 2 theta all over 2. And again, I know that that cosine term is going to go away. That should actually be 4 theta. And this will be 1/4 plus 1/8, which, and now this is the part that I actually struggle with, 3 pi over 8. Okay. So this is equal to 2 pi for the first one, minus 8/3 times 3 pi over 8, which is just pi. That's pi. Yay. Okay. And now for part B, it wants us to find the x component of the centroid. And it tells us to use symmetry. Normally I don't like skipping to a symmetry argument because I like to show you guys the math. But this one, the math is ugly. We're not going to do it. We're going to use symmetry. And so what we'll do is we'll say, okay, along the base, well, actually what we'll say, if we look at this region here, and if we flip it around the x-axis, the region doesn't change. It's symmetric about the x-axis. And because of that, let's say that the centroid were at some other point. Let's say that it were, put it in blue. Let's say that the centroid were here. Well, then when we flip the shape, the centroid would go over here. We know that those two are the same shape, so this would tell us that the shape has two different centroids, which isn't correct. And so when we flip it about the x-axis, it has to stay in the same spot. And the only way for that to happen is if the centroid is on the x-axis. So this tells us that the x component of the centroid is 0. And that's that worksheet. I think that's all I have to say. Yeah.